Hi everybody, Justin here from today's video is the second video from section 5 gases, and we're going to talk about 3 gas laws, and then we're going to combine all 3 of those gas laws into something called the combined gas law. We're going to define the universal gas constant and then convert our combined gas law into the ideal gas law. So let's take a look at the first gas law, shall we? The first one is Boyle's law, and pressure of a gas times the volume of a gas is always going to equal to some constant K. The value of the constant is not important, and Boyle's law refers to the pressure-volume relationship of a gas at constant temperature. So if you take a balloon scenario, if you were to see my hands, if you were to take a balloon and squeeze it, as the pressure of something increases, the volume goes down. So that's an inverse relationship. So what I'm trying to say here is that if pressure times volume, or PV, equals some constant K, well, if P increases, V decreases. If pressure goes up, the volume goes down, and vice versa, of course. So this is an inverse relationship, or we would say that P and V are inversely proportional. So if I take a situation 1, P1V1 equals K, situation 2, P2V2 equals K, and I can have P3V3 and so on. But if we just take situation 1, and then we tweak the system, or we change the conditions, so now we have P2V2, they're both equal to the same constant K. So the usable form of Boyle's law is P1V1 equals P2V2. That's why I got a big box around it. Let's do an example. Consider a 1.53 liter sample of SO2 gas at a pressure of 5.6 times 10 to the third pascals. If, there's the word if, there's the conditional, right? If the pressure is increased to 1.5 times 10 to the fourth pascals at a constant temperature, what's the new volume of the gas? Okay? Well, in reading the example, we know that the relationships they're talking about here are pressure and volume. Constant temperature is the condition we need. So it's P1V1 equals P2V2. I plug in my P1s, my V1s, and my P2, and I solve for V2. 0.57 liters, 2 significant figures. The volume, the pressure went up, which is why I expected a volume less than 1.53 liters. The V2 is 0.57 liters. Second law I want to talk about today is a relationship between volume and temperature. V over T equals K at constant pressure. The other variables held constant. The temperature must be in kelvins, okay? Always think of temperature in kelvins. If I think of the balloon scenario again, if I increase the temperature of a gas, as I increase that temperature, well, the volume is going to increase. You ever see like a hot air balloon when it's limp, it's all flat and laying out, and then you see them turn on the fire, and as the fire heats up the air inside the collapsed balloon, the balloon starts to expand, and they get the balloon ready to be used as a hot air balloon. That's an example of Charles' law. If my temperature goes up, my volume is going to go up. All right? So Charles' law, the relationship between volume and temperature, is a bit different than it was for Boyle's law. Here we have a fraction, V over T equals K. All right? So what can we say about Charles' law? Well, if V over T equals K, then as the temperature increases, the volume is also going to increase in order to keep the value equal to some constant K. Right? So temperature and volume are directly proportional in this case. Now here's our situation 2 and then our situation 1. Situation 1, V1 over T1 is equal to K. Situation 2, V2 over T2 is also equal to K. Since they're both equal to K, I can just set them equal to each other. And this gives us the usable or workable equation for Charles' law. 3 stars around it. This is what you want to remember. V1 over T1 equals V2 over T2. Constant pressure. That's the Charles' law that we'll be using when solving problems. Example. A sample of gas at 15 degrees Celsius and 1 atmosphere of pressure has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atm pressure? You notice the pressure stays the same, or in other words, it's constant. That's the condition we need. And what they're talking about here are what volume are we going to have the gas occupy if the temperature is increased? Well, if the temperature goes up, the volume is going to have to go up. We expect a value greater than 2.58 liters. First thing we do when we see Celsius in this entire chapter, this entire section 5, take all the Celsius values, convert them to Kelvin. So I've done so. V1 over T1 equals V2 over T2. You plug in all the proper values, and I have V2 that I need to solve for. And in math, when we see a proportion like this, we say cross multiply and divide. So if I cross multiply 2.58 times 311, divide by 288, I get my value for V2. And that would have the proper number of significant figures. Don't forget your units. The units for that last problem were in liters. The third law. We had Boyle's law. We just did Charles' law. This is Avogadro's law. Avogadro's law states the following. For a gas at constant temperature and pressure, the volume is directly proportional to the amount of gas, or to the number of moles of gas. So volume V, capital V, right? V is in Victor, volume, and then we have moles, N. Well, if they're directly proportional, then V over N is always going to equal some constant K. Value of the constant does not matter. So V over N, where N is the number of moles of gas. So the greater amount of something in moles, the more space it's going to occupy. All right? Now I know we're talking about gas molecules and the volume is mainly empty space, but just think of it kind of from a perspective where we're holding the temperature and the pressure constant. So the more I have, the more space it's going to take up. Right? As my number of moles goes up, or as N increases, the volume also increases. In other words, they are directly proportional. What I'm getting at here in the if statement is that in situation 1, V1 over N1 equals K. Change the conditions to situation 2, V2 over N2 is also equal to K. Set them equal, and you get with 3 stars down there, that box is your usable or your workable version of Avogadro's law. V1 over N1 equals V2 over N2. All right. Next page of our notes, what we're going to do after this example is we're going to summarize the 3 laws. But first, let's do an example. Suppose you have 12.2 liters of O2 gas. In that 12.2 liters of O2 gas containing 0.50 moles at a pressure of 1 atm and a temperature of 25 degrees Celsius. If, there's the conditional, right? If, moving into situation 2 now, if all of this O2 were converted to ozone, O3, at the same temperature and pressure, what would be the volume of the ozone gas? So they want us to find the volume of O3. But we don't even have O3 at time 0 or situation 1, right? So we have to write down a very simple equation where we convert O2 to O3 and then balance the equation. So the little bullet point here, it says asked for volume of O3. Assuming this is V2, we need to calculate N2 for O3, not O2. So before applying Avogadro's law here, we have to do a simple chemical reaction, balance it, and we're going to start with what we're given, put it over 1 because we do assume all the O2 is converted. 0.50 moles of O2. For every 3 moles of O2 in the balanced equation, there are 2 moles of O3, 0.33 moles of O3. That's how much O3 we have at the end. So that's our N2. V1 over N1 equals V2 over N2. We then plug things in. So we got 12.2 liters over 0.50 moles equals V2 over 0.33 moles. My V2 has the same units as V1, 8.1 liters of O2. Okay, and that should be O3. So I apologize for the typo. All right, now let's put those 3 laws together. So here's what we're going to do. On the left-hand side of this page of our notes, I'm just going to write down all of the 3 laws that we've just done. And then we're going to kind of combine them and manipulate all the numerators and denominators together into one numerator and one denominator and see what we get. So Boyle's law. Boyle's law was the first law we did today. We got P1V1 equals P2V2. Or you could say that PV equals K. All right? Charles' law was the second law that we did of the 3 laws. And this one was V1 over T1 equals V2 over T2. Or you could say V over T equals some constant K. Third one, Avogadro's law. This one was held at constant pressure and temperature, and it's V1 over N1 equals V2 over N2, or for our sake here, V over N equals K. So PV equals K, V over T equals K, V over N equals K. Well, the P and the V are always in the numerator, while the N and the T are in the denominator. So if I combine that, I get P1 V1 over N1 T1 equals P2 V2 over N2 T2. This is my combined gas law, and I've put a box around the one that we use the most when we're asked problems in chemistry to solve for. So it says on the right hand side, the one that's not boxed, PV over NT equals K, some constant K. Well, if I determine, I say, hey, I'm going to make K equal to 0.0821 liter atmospheres per Kelvin per mole, which I'm writing down right now. That is the universal gas constant. So if I set K equal to the universal gas constant represented by a capital R, I would have rewritten PV over NT no longer equals little k, but it equals R. Cross multiply, set them equal. I get PV equals nRT. So in this page of notes here, we've derived our combined gas law, and then we've also achieved the ideal gas law, PV equals nRT. One more blurb here on PV nRT before I let you go. The ideal gas law, if you look at the units of R, R is a universal gas constant, and the value isn't just 0.0821. It has certain units. R is 0.0821 liter atmospheres per Kelvin per mole. So the liter atmospheres per Kelvin per mole unit, that forces, for the first time, it forces everybody to have specific units required. Pressure must be in atmospheres. Volume must be in liters. N is pretty much always in moles anyway. And the temperature must be in Kelvin. Now, prior to this, the temperature was the only one we had to always keep in Kelvin. But with the ideal gas law, your pressure, your volume, your moles, and your temperature all have to have specific units. All right. So next time we'll continue with a bunch more practice on ideal gas law and combined gas law.